In the last presentation, we looked at the rules for drawing structures, building on what we know from Lewis' theory. Carbons have 4 bonds, nitrogen 3, O's, oxygens 2, and halogens 1. And we were able to understand the rules for shorthand to draw what we call skeletal structures. But the second task is moving beyond just letters and lines, the frame that we sort of look at as we start understanding structures, looking past that to seeing not just letters and lines, but orbitals, wave functions, things that quantum mechanics informed us of in the late 19th century, early 20th century, the 1800s, late to early 1900s. Much developed in terms of our understanding of electrons. No longer would we look at just a line as 2 electrons bonding 2 atoms. That changed. So let's go into the second task. This presentation, the second of 12, will really look at just the theory of hybridization, but it starts with our understanding of electrons as waves. It was found through the work of physicists that if we looked at the atom, the electron behaves as both a particle and a wave. This was ground shaking, earth shatter, I guess. This was seismic as far as the shift in our understanding of subatomic particles, particles that are within the atom. Electrons are very small, and their behavior became very, I guess, difficult to understand because it wasn't as if it was a particle going around a nucleus like a planet around the sun. That didn't work. There was too much that was coming out of the work from physicists that said, no, there's something else going on that defines these electrons. What it turned out to be is that we treat these electrons not just as particles and not just as a particle riding on a wave around the nucleus. No, it is the wave. Boom. Like here's my nucleus. It's not a particle riding on a sinusoidal wave. No, it is the wave. It's woo, 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 woo. That's my sound for a wave. Woo, 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 woo. Now in the background, you hear Journey playing, and I thought, any way you want it, that's a song that may say something about waves being in any way they want to be, and music has its sound waves. But one thing that really also helped us understand the electron, not only its particle-wave duality, but that it was confined. It was confined as a wave, so it couldn't be any way you want it. It had to be continuous around a focal point, around the nucleus, so that boom, boom, boom sound for my wave had to be of a set wave. Because if I come back to this point right here, let's say I'm standing or I'm up at some point and there's a wave value. If I go around the nucleus and come back to that point, the wave has to come right back to that value that describes the wave, coming in the same slope. It has to have continuous behavior, just like we know waves have. They are continuous. We don't go to the seashore and see waves all of a sudden jump from a trough to a crest in a discontinuous way. No. These waves are continuous, and what we did is we had to put them around the nucleus. That caused quantization of electrons because we could only have certain types of waves. You know them as 1s, 2s, 2p, and we really just talk about 90% probability of finding the electron is in this particular shape or space, but the wave continues on. We just wrap it up and say most of the electron density can be found in some certain amount of the space around the nucleus being at the center here, and these being waves for a p orbital, and waves, this being the nucleus, for a 2s. If you didn't catch anything in this last 3-4 minutes, just catch this. Electrons started to be understood as not just as particle but as wave. That was the first breakthrough. Second, because of their confinement around the nucleus, so we can take that wave and in a sense consider it to be wrapped around the nucleus, certain shapes came out of that. So a wave, confinement of the wave, bam, quantization. Specific energies tied to specific wave functions or orbitals for those electrons. That's all I want to say about that. Now let's build on this idea of electrons occupying waves or orbitals. So principles were started to develop as to how we fill up these orbitals. The Aufbauer principle moved from lowest energy to highest energy around a nucleus if you're putting electrons in. So for nitrogen, having 7 electrons total and 5 valence electrons, meaning on the outer shell. Even the word shell, now we think of shells in terms of 2s and 2p orbitals in the outer valence shell. Well, for nitrogen, we then fill up by Aufbauer principle from lowest energy to highest energy orbitals. We have 7 electrons. We've gone in with 2 in the inner shell, 2 more for the 2s, and now with 3 electrons left, by our Hund's rule, we're going to fill up degenerate orbitals or equal energy orbitals, 1 electron each. That should be right here. And these horizontal lines are representing the orbitals. The Pauli exclusion principle was developed out of quantum mechanics with some spin up, spin down designations for electrons. And two states, spin up or spin down, could be present for a particular orbital. So only 2 electrons can be in an orbital. Well, of course, that fits well with Lewis theory, where we have 2 electrons for every bond. Bonds are going to be made up of a orbital, and we'll see that you can only have 2 electrons in an orbital, no matter what type of orbital you have. So that's the big breakthrough. Again, as waves are electrons behave as wave, and 2, they're confined. That generates these particular wave functions, the quantization of energy, and we fill up those orbitals in a particular way. The picture of the atom changed from 1920s, 1930s. It developed immensely. Pictures then of electrons and molecules changed. So let's make some bonds now with orbital theory in tow, or in thought. There are 2 ways we can incorporate this orbital-based bonding theory. We can consider valence bond theory, which just looks at the overlap of 2 orbitals, whatever they might be. In this case, we have 2 1s orbitals that are colliding, and we're considering the amount of overlap between them to be proportional to the strength of the bond. 2 coming together to form 1. New picture of, we're going to draw the nuclei, the hydrogen molecule. This being our line, we now see not just the line, we see orbitals overlapping when we see a hydrogen molecule. That's the model. These bonds are involving electrons that are overlapping such that the electron overlap is between the nuclei. When that occurs, we have a sigma bond. Single bonds are always sigma bonds, having head-to-head overlap between the nuclei. They are stronger than pi bonds. So let's look at pi bonds. Pi bonds, we're going to use, you can use valence bond theory to look at pi bonds. We're just going to use molecular orbital theory to get a sense of to get an understanding of what pi bonds are like. So I'm going to just use another theory. We could have looked at 2p orbitals overlapping according to valence bond theory, but we could also look at any overlap of orbitals using molecular orbital theory. Now, molecular orbital theory is different from valence bond theory in that we both consider the overlap, the amount, just like we did with valence bond theory, but we also consider the sign. Now, remember how on any wave at the ocean you have a trough and a crest, a low and a high. Now, we have to have that sort of property for any wave. A crest, trough, a node, those types of terms have to come out. So that's what we kind of have with these p orbitals, is we shade in one side to sort of represent, you might say, the trough in a wave, and the other side to represent the crest. Now, I'm not going to go into any greater detail than this, but just to say, please understand, it's a mathematical description of the electron, this shaded and unshaded side. It really has no physical significance. Crest and trough have some physical significance in that we're looking at this as the height from the center of the Earth. Well, that's not what we have with orbital theory and electrons. We just have the mathematical underpinnings for the definition of a wave that we have to use if we're going to use MO theory. And we just designate those two sides of a p orbital as shaded, unshaded, psi values being different, or the wave values being different, crest, trough, positive, negative. Now I want to stop there and just say that's what we mean when we say the sign of an orbital. The sign of it, it has two different sides of a p orbital according to their sign, their crest and trough. Now, there's more you can say about that, but for sake of time we'll leave it there and just say, as we look then, as two p orbitals start to collide, we consider both overlap and sign. We can have constructive interference, gray to gray, crest to crest, that would increase the amplitude of the wave, and that would give us what we call constructive interference. However, if we flip this over so that the white is down and the gray is up, we would have destructive interference, what we see up here. So let's stop with our discussion of molecular orbital theory just to say this. Molecular orbital theory looks at both the amount of overlap when two orbitals are brought together, the amount of overlap, but it also considers sign. And the number in is always equal to the number out. The number of new molecular orbitals, which we have here, is always equal to the number of atomic orbitals that came in to interact. So number in is always number out. And they're either considered bonding, this would be considered anti-bonding, and this one down here would be considered bonding if there was ever an overlap where there's equal destructive interference to the amount of constructive interference, we would call that non-bonding. These are typically pictures, these are molecular orbital descriptions that I've drawn here. These are not typically seen until the end of the discussion on organic chemistry. Typically you'll see early in most books valence bond descriptions. So let's go ahead and move in that direction, just looking at the amount of overlap. So now with an orbital theory, we can look at methane, which before orbital theory, all we knew is that there were two electrons between carbon and hydrogen in this CH4 structure. But now we change that picture. We see a p orbital, three of them. Let's call this the PZ and our PY. This might be the PX, and the one on the axial here, the PZ. Those are the three p orbitals, and this one here in the center, we're just showing it as a s orbital. And these are all the two. This is carbon, so we have the 2s and the three 2p orbitals. So that's the picture we now have instead of just a Lewis structure. That picture of the carbon atom now brought together with 1s orbitals from hydrogen, we might propose that we get a bond between a PZ and a 1s for hydrogen, another 1s from a hydrogen to a PY, and then the PX with another hydrogen, and the one hydrogen with its unpaired electron has to make contact with the 2s orbital of the carbon. So we'd have three bonds of one nature and one of a different nature, but that didn't pan out in the lab, you might say. In the lab, it was found that this picture doesn't work. There are four bonds equal length at tetrahedral orientations, and they were all of equal energy. This picture didn't work. This means that four equal bonds were formed. from the lab, that's what was indicated. So we had to figure out an answer to how we could keep orbital theory, but get a better picture of the bonding within methane than what we see here. Well, hybridization, or Linus Pauling, to the rescue. And we're going to look at just 2 more slides to show how this theory of not only orbital theory emerged, but how Pauling, through hybridization, a tweaking of orbital theory, was able to better explain the bonding we see in methane. So what I want to do is just sort of change the colors a little bit, but I still want you to think of the P orbitals around a nucleus and the carbon's 2s orbital around the nucleus, but we're going to just separate them for clarity and change the colors. So here's that 2s, here are the 2p orbitals, and we've just separated them just for clarity so we can pull those, just to look at those different orbitals in an easier way. So what Pauling proposed is he said, look, what if we were to take, and since these are just equations that define a wave around a nucleus, and again the blue and the red represent signs, the psi values, the crest and trough nature, what if we were to have waves mix? Before it goes to bonding, or as we consider bonding, have these atomic orbitals just mix like waves do on water. Consider new waves through that mixing, and then go to bonding. So what he proposed was S, take that into the mix, have it mix with 3Ps, sp3, hybridization to give us 4 new atomic orbitals. But they would no longer have true S character and just true P character. They'd be mixed. Like a daiquiri. You mix an orange and a banana in the mixer, they lose their integrity and they become something through their combination. These are 4 separated atomic sp3 hybrid orbitals. And we can then, after that hybridization, kind of in a sense, consider the electrons that can be put back into those orbitals. They're just mathematical equations. And then take carbon's now 4 new sp3 hybrid orbitals and use them for bonding. Better bonding resulted, or theory would show that the bonding, the amount of orbital away from the carbon's nucleus, was available for bonding. It gave us tetrahedral orientation for bonds of equal strength. It worked very well. So those 4 sp3 hybrid atomic orbitals are considered tetrahedral in orientation and readily accessible for bonding. So now this picture changes, and I apologize, there's another color change. So we went from what was the wrong picture, hybridization. Linus Pauling proposes we have 4 sp3 hybrid orbitals that can now bond in a way that gives us tetrahedral orientation of the hydrogens. They're in red here. When they come in, they're coming in at these new orbitals. Remember, these are now new atomic orbitals. They are 4 sp3 hybridized atomic orbitals, and they are ready for bonding with the hydrogen. And so we bring those hydrogens in. They bring their 1 electron matched up with the carbon's electrons that are 1 for each sp3 hybrid orbital, and we get a match between the theory, orbital-based theory, and experimentation. Hybridization was key. Amended by the concept of hybridization, orbital theory could match what we saw in the labs. It's a great theory. It should be hybridization. I'll stop there. There is no we'll bring in the third recording, some discussion of how we can designate hybridization for atoms. This was just a recording to explain the phenomenon, or explain how hybridization developed out of orbital-based theory to better explain the data from the lab. Just a couple of notes to end with. sp3 hybridization of carbon allows for the best head-to-head overlap, or sigma bonding. Remember how we said in that mixing, these are in green here, but they're in red and blue here, the orbital sticks out from the nucleus, allowing for good overlap with the hydrogen. So I apologize, the colors are changing. This is for the carbon, has its 4 sp3 hybrid orbitals. Of course, they're still around the nuclei. They're just shown in green here. They overlap with the hydrogen in a head-to-head manner. That is giving us a good bond. Carbon, nitrogen, and oxygen can all undergo this hybridization to give us better bonding. And we want to remember this: single bonds for C, N's, and O's are always sigma bonds. Single bonds are always sigma bonds, and sigma bonds are made using hybrid orbitals, sort of an A to B to C. Single bonds are sigma bonds, and sigma bonds are made using hybrid orbitals. Bye-bye.